Thank you all for coming. So it's my pleasure today to share this kind of regular, bi-weekly seminars on machine learning. I'm Adrien Pichon, I'm the coordinator of the Unified Bioinformatics Center, and I'm together with Kunyi. We are actually who's the coordinator of the complex systems studies. We are organizing those meetings. And today, well, we have a full session on natural language processing, so it's my pleasure to introduce Thomas, who's a good friend. We actually know each other from daycare. No, from daycare because our children we're going to the same daycare and we're sharing the same passion for beers. He likes to craft the beers, I like to drink them. Actually, you also do like to drink them. So that's where we started sharing some interest in science, chemistry of the beer. Thomas has a very interesting background. He did a PhD in statistical and quantum physics, Pierre-Marie Curie. He has a law degree from Paris Sorbonne. And I think despite all the efforts that he's putting in science, he's mainly well known for creating a magic sandbox for his son, for his 3-year-old birthday. I think you made it to the first page of Reddit, or the second one, I don't remember. But that was really like it's his best achievements. So it's an augmented reality sandbox. Anyway, I do like also to play with it. So, well, Thomas, thank you for being here and for introducing us what you're doing now at Hugging Face.
Okay.
So,
yeah. Thank you for inviting me, Adrien. Thanks everybody for being there. So today I'm going to talk a little bit about natural language processing. Actually, the topic will be a bit wider than what was advertised because when I was preparing the slide, I actually realized that maybe most of you are not really familiar with natural language processing as a field, so I was starting with general introduction to get you all on board, why we are doing that, why is it interesting, why am I spending my days doing that. So just a little bit on me, I'm Thomas Wolf. I work for a New York City-based startup called Hugging Face. Hugging Face is developing conversational agents, which is like a bit like a virtual pet that will talk. And everybody's in Brooklyn actually, but me, because my wife works at the university, so I'm in a chat. So I have the pleasure to be there and present what we are doing with you. So let's start with a quick introduction to natural language processing. What's that? So maybe just one question. Who here is familiar with natural language processing? Who among you? Yeah, okay, just one. Okay, so it's great that we start from basics. So the basics. Since the dawn of ages, humans have been talking, and if you haven't read this great book called Sapiens by Yuval Noah Harari, you should do that now. I think it's a very interesting book about what is humankind, how did we become like the dominant species on Earth. And like the first part of the book is about cognitive revolution, which is basically sparked by language, human language, which is, according to Yuval Noah Harari, something like very specific among all animal species, which is like very flexible tool we use to communicate, to convey information about objects, concepts. And actually, what Yuval says that it's the very specificity of human language that we can talk about things that does not exist. Like we can think about stories, we can talk about things that are that we are creating and creating stories with languages. So that's this very unique thing that we have, and that's today it's used to store basically all human knowledge, like scientific articles, books, encyclopedia, discourse, everything is stored as language, human language, and written form, most of it. So that's why we are very interested in that. And for us working in the artificial intelligence field, like almost everybody agrees that at some point we need to tackle language, so that if we want to build machines that have some form of artificial intelligence, then we have to learn to understand and use language. And it's basically the best way also for them to learn, if they want to learn on themselves. So what I call natural language is the language we use to communicate as human beings. And we say natural language because there are a lot of other languages that we call usually formal language, like logic, mathematics, programming language. So all of them, they are also languages, but they are less flexible. We cannot express anything in mathematics, like love, dreams. It's very hard to put them in mathematics. So what we are concerned with is natural language. And the exact field I'm working in is natural language processing, which is how can you program computers so that they can process and analyze natural language. So it's a bit like an engineering field, right? It's like building planes. We try to build systems that can be used in real life. And so it's built on the shoulders, it's standing on the shoulders of several science fields, which are listed the major ones here. So cognitive science, linguistics, computational linguistics, machine learning, artificial intelligence, they all have their own questions, they all have their own thing they are trying to understand. For example, it's the mind for cognitive science, what's the language for linguistics, how does language appear in our history, also how children learn language. So computational linguistics is a bit more focused. It's how can we build computational models of language. Like, can we implement language in a real form, like behind the theory? Like maybe you know Chomsky theory, this kind of thing are very theoretical. And computational linguistics is that, can we put that in computer, like use that, or can you compute with that? Machine learning is this very wide field, which is how we build statistical models for phenomena. And artificial intelligence also is this umbrella upon everything when we want to replicate some aspects of natural intelligence. So NLP is like gathering all these theories together and trying to put them in practice. And there's also some feedback loops, because when you put that in practice, then you learn that some theory just cannot work, because it doesn't work. So there is some interesting interaction. And in our company, for example, we publish research in the same conferences than the computational linguistics and also artificial intelligence, for example. So, like, the fields are kind of blurry.
Thomas, can I ask you a question?
Yeah.
So you're making the distinction between natural languages and formal languages, and now also natural intelligence and artificial intelligence. So why not actually a formal intelligence? Or do you mean that because it's artificial, it can be as flexible as a natural intelligence, while the language should not be?
So here it's about fields, like scientific fields. Okay? So artificial intelligence, you have some people are trying to reproduce language, which is what we are doing. But there's also the other thing to natural intelligence. So natural intelligence is not exactly the same as natural language, right? It's intelligence in humans. And artificial intelligence is like when we build this kind of thing. And we can reproduce many things, like for example, computer vision, like recognizing patterns, like seeing this is a chair, this is camera. It used to be something that we thought was like natural intelligence, almost not reproducible. Today we can do that, and it's called AI, it's called artificial intelligence. So, but that's not language, right? It's another form of intelligence. And and then there is no real definition of formal intelligence, I think.
No, because I was just thinking the formal languages, they indeed lack the flexibility of the natural language.
Yeah.
But do we think that with artificial intelligence we will reach the same flexibility as we had in so-called natural intelligence? So it's just a question for you.
That's the goal. That's one of the goals. Usually we call that AGI, which is artificial general intelligence, which is can be something that would be. Well, then there's a lot of questions like something that would be self-conscious and all the thing. I'm not really concerned with all these things, but I think they're interesting. There are also a lot of interesting things on formal language, but oh, sorry, I'm back. I don't have time to talk about everything. So, formal language, you missed a lot of things that we would see. For example, in dialogue, you have pragmatics like understanding the emotion. Sometimes you say something that is exactly the contrary of what you want to convey as information. So there's a lot of things in natural language that you don't have in formal language, which make them more interesting for some people. So back to natural language processing, we have two main tasks, two main things we are interested in. They overlap, you can use both of them at the same time. So one is natural language understanding, which we call NLU, which is you have a text as an input, and you want to process something from this text. So this is super interesting, I think. For example, one example is like extracting information from scientific publication. Like today, we are publishing a lot of papers, like millions of papers per year. There's nobody can read them all. Everybody reads very small field that is interesting too. And so the question is, could we have a computer that would read this, like extract information? Like for example, in cancer research, we say, oh, you're talking about this protein, but I also read this paper from chemistry who's also talking about this protein, and then tell you, well, you should make a link. So this is, I think this is super interesting, and this is an area where AI could really help, like science in general, like helping them make correlations. So a lot of people are working on that, and that's a good example of NLU. And basically, it's also the basics for many downstream systems. Every time you have some text as input, you want to have an NLU system that will extract information. So business intelligence, extracting the name of the society from Twitter or something like that. And the other thing is natural language generation, where the text is an output. So the main usage is to communicate with humans, like a dialogue thing. And another way to use that is also to store information in a way that could be read by humans. Yeah, just a definition. When I talk about text, I mean natural language data. And when I talk about data, I talk about all the rest, like numbers, graphs, all the things that are data, speech. So today, we focus on natural language generation, which is...
Can I ask one?
Yeah.
You say speech is amongst all the rest, so that's not natural language?
Yeah, it's, I mean, the auditive signal, like the acoustic signal. Right? So usually the first step is you convert that in text, and then you use the NLP, natural language processing system. But yeah, and usually we have, that was one area that really helped a lot. Actually, natural language processing. Speech was one of the areas where we developed some other thing I'm going to talk about later. So yeah, even though I think natural language understanding is very interesting, today I'm going to talk about natural language generation, which is even more interesting, I think. This is a bit packed, but let's just go through it very quickly. There are a few things that are interesting. So general interest, I talked about that earlier. A lot of people like me that are interested in this field think that if we understand how we generate language, we actually will understand a lot about how human cognition works, because it's such a fundamental way that we think. For example, a lot of people are thinking like talking to themselves in their head, so it's like a fundamental process. So there are cognitive research that have been very, I wouldn't say fruitful, but people have in cognitive science have worked on that since a very long time, and also in linguistics. And two things that are maybe more funny is how this can help the artificial intelligence field in general. So, which is the second part, and it can actually help us to do what we call understanding. Today we have more and more algorithms that take decisions that have effects in our lives. For example, you want to apply to a job, there is like automatic screening by an algorithm that say, we keep this CV, we don't keep this one. And these are usually like black box system. You don't know why the algorithm took this decision. And it's more and more a problem, because the more we have algorithms like that, which are black box, the more we are losing all the control, basically. And a good example is how humans do when you take a decision, like you decided to go buy some bread, and I can just ask you, why did you do that? And you would answer, yeah, there was no more bread left, or I don't like this kind of bread, I want to buy another one. Okay. And one idea was, is like, what if the AI system would work like that? We could just ask, why did you not keep this person as a possible potential hiring, for example? So that's very, I mean, far-reaching, but it's something people are working on. And another thing is the problem of data availability. More and more, like, our AI system requires very huge amount of data. And usually what we do is that we annotate this data, like we write, this is a good CV, this is bad, or like this is a good tweet, this is a bad tweet. And it's very expensive to do that for huge amount of data. So there's a lot of research called transfer learning, on which we actually in the company are working on, which is based on this idea that if you know how to generate language, you know a lot about language, and you can actually maybe learn on your own without having people to annotate all the examples. It's a bit like your kids, you don't say every dog, like this is also a dog, you just show a few examples, and like kids are able to generalize. So this is also something we try to do with NLG. And just to summarize, here is the general ecosystems. I talked a lot about science. These are the applications. So machine translation is a big application. Just we'll talk about that. Summarization also. You take text, extract summaries. Image captioning. It's already actually used in Facebook, I think. If there is some picture don't show you a big caption, that's automatically generated. Business intelligence, how you take a lot of numbers, put them in some short summary. And entertainment is where we are, game industry. Can you have the artificial intelligence in your game talk to you without this being scripted? And so there's all this. And something very cool too is art. Like, can you improvise with an AI? So we have somebody we're working with who is doing this. Like you talk, the AI response, and like it's not scripted. It's like live response that try to adapt to the artist. So use as a tool. It's really cool, I think. So how does it look in practice? An LG system. So it looks like this. You put data, you put text, and you generate text. So all is in the big box in the middle. So these are just a few examples. Translation, you take text in one language, you put text in another language. News article to a summary. And people are actually trying to do what they call multitask system that would do a lot of these tasks at the same time, that would be able to do all these tasks. And, but yeah, the big question is what's in the central box. So a bit of history, the first thing people thought was this very engineering approach. You have a complex problem, how do you do that? Well, you split it in some simpler task. So you think a lot, well, how does it work? So here you would have a text planner that would say what you generally want to say. You want to talk about this bird. Then the sentence planner that would say, okay, we need 3 sentences to talk about this bird. And then the realizer, the last box, will say, okay, the first sentence will be like this, second will be like this, third will be like this. So these are good things, like you can iterate on each module. For each task, you can brainstorm that and say, okay, how do we decide how many sentences we need for each topic? It's also a bad thing because obviously that's not how humans work. Like, I'm not planning and say, oh, I will need 4 sentences to say that, and then building my sentences. That's just not how we do that. So obviously, there is something we're missing. Most of the time, we are like free rolling on language, and then we grab something and like, oh yeah, I wanted to talk about that. So people are increasingly departing from this approach, but it's still like most commercial systems, still the dominant approach. So how could you do otherwise? Well, the general way to see that is the canon-based approach, where you are in some states. Like I've started to talk about starting a sentence, I'm in a general state, and now I take an action, which is next word. I'm going to say I say this word, and I'm in the next state. Okay? So it looks a bit like you're playing chess, you know, you're like moving, and make you thinking like, I should say this word, say this word. And you have a different way, where obviously the question is, what are your states, and how do you select the action? And in the old days, the states were discrete, so there were like finite number of things you could say, and you would move them using rules or plan-based approach. And the recent twist is something called reinforcement learning. So if you haven't heard about that, I won't go into this, but it's like how AlphaGo works, basically, and all these kind of game things work. And the other thing, which is what I'm going to talk about, is when you model the states as a continuous dense vector. So you have just a big vector of numbers that's stored in some kind of mathematical latent space where you are in your discourse, and you're using a neural network that takes this space as input and generates the next state and the action, which is the word. So that's very general, but we go in deeper. Now, how you learn to generate? You have 2 approaches. The unbased was like what we did for decades, which is you write yourself the rules. Again, you think a lot, well, what should I say? What should my AI say? And you write all this. And what we're trying to do more right now is statistical approach, where we have a big data sets and we just try to learn the parameters of our system from these big data sets. Okay, so let's go in practice. With an example, which is what we're doing, which is an open domain conversational agent. So it's something that can talk about any topic. So it's a really tough task. So usually, what I'm going to talk about today is the restriction to chit-chat settings, which is very short conversation. And we call that small talk, which is you don't go very deep, like you ask, have you seen a movie? But you won't ask, what was the plot about, or how did it end, or what did James Bond do after that? Just small talks, quick talks.
Excuse me.
Yeah.
Why we can do the natural language generation in a top-down approach? Because you said it's a bad thing about natural language generation.
This thing?
Yeah.
Why did I say it's a bad thing?
Yeah, you said that.
Oh yeah, because we don't really, well, the problem is in this top-down fashion is that...
because, for example, in latent legal allocation, we can do that.
In what?
In the LDA method from David Bloy,
yeah,
we can do that from the top down. We can, if we have the topic distributions.
Yeah, exactly. So this is this is well, okay. Yeah, this is LDA is this kind of approach. I mean, I'm not saying LDA is bad, right? But I do think it's not the best one for natural language generation. But it's good for classifying documents. It's really good. But when you use that for classification, for generation, this kind of method, I usually not so good. But it depends, right? In LDA, you have a very shallow hierarchy. Usually, you just have topics, and then you have the words. Yeah. So here, it's rather okay because the way we speak is also a bit like that. Like we have a topic, and we're talking about that. What I'm saying is bad here is usually that you try to build a hierarchy that is too deep, and that you manually engineer in your head. Like, for example, starting from topics and then saying, having something that say how many sentences you want to generate and then generate sentence sounds.
So we can do that?
You can do that, yeah, but it sounds a bit unnatural. And in practice, you will need feedback loops for this. You will need something that say, for example, when you generate sentence, they would say, oh, actually, I don't need a sub-sentence because 2 sentences are enough. And you don't have this kind of thing. But you have architecture that are based on this, but more complex, that allow feedbacks that say, oh, that was a mistake. We can avoid that.
Thank you.
And also in planning-based approach, you have hierarchical planning, which is like you have a goal, general goal, like for example, a bit like people do also. You want to convince somebody about something. This is your general goal. And you can build sub-goals, say, okay, I'm going to start talking about his family, and then we're going to talk about money, and then we say, oh, by the way, I need some money, maybe you can build this kind of hierarchical goal planning-based approach that makes sense, and that we use in some context. So it's all, everything's not black or white, right? So, yeah, so this is chatbot, what we call chatbot, basically. And we're using this statistical approach, which means we're building a data set to learn things. So this is an example of a data set for chit-chat. So this one was published last year, personal chat, it's called personal chat. And let me just show you quickly how it was built. We use Amazon Mechanical Turkers, which is a website where people are performing like intellectual tasks for a cheap amount of money. So here the task was to talk with somebody else, which is not the worst task that you can be asked to do. So they were paired by 2. So they don't know each other, right? They are just logging on this website on the internet. And each of them is given personality that you see on top. So like, I like to ski, my wife doesn't like me anymore. So these are like 4 to 5, the simple sentence that describes somebody, general way. And they were asked to talk to each other and get to know each other. And they had to pretend they were the person in the personality, right? And so, they asked other people to do that. That resulted in a data set of 10,000 dialogues with quite a lot of utterances. What we call utterances is a single turn of conversation. Like you talk, you can say several sentences, and then you stop, and the other starts. new utterances. So it's more than a sentence usually. And that's the data set we use to try to learn how to conduct a conversation. Okay, you see what you're doing? So how does it work in our case? So you remember, it was just the general architecture, we have knowledge base, we receive input utterance, and we generate utterance. So in these data sets, our knowledge base is the personality, and usually the history of the dialogue, plus some common sense knowledge. We get the previous utterance, and we generate the next utterance. And everything is in the dialog system. So let's dive in the dialog system. Here I want to dive a bit in a really like deep learning kind of thing. So it's an experiment to see if you can follow me. So it's going to be suddenly very hard. So we use what is called a transformer model, which is taking the beginning of a sentence and generating the next word. Okay, so it's like the thing I was saying. We are in this state, which is like we have this beginning of sentence, and we generated action, which is the next word. Okay. So how does it work? So for example, this is the beginning of sentence. We have seven tokens, 7 words. Nobel Committee awards Strickland who advanced optics. Well, that's from a newspaper, so it's not a chat. So the first step, we convert these words in vectors, because we're using these continuous dense vectors. So each word has a vector. And then what we want, actually, to generate the last word, we would like to mix these words together, so we build some meaning, some general meaning of the sentence. Okay? And the way we do that is by comparing each word to the other one. Like, optics has no real meaning alone, but when you combine it with the neighboring words, then you acquire its meaning. Okay? If I say blue, you're like, yeah. But if I say my dog is blue, then you have a really great idea. Ah, yeah, it's a dog that's blue, right? You have to combine all this. So we do that by using some database approach. So first, from each vector, we generate 3 vectors, which is a query, a key, and value. So if you're familiar with database logic, it's the same idea. And then we will, let's start with novel. Let's see how we can combine novel, how we can combine novel with the knowledge of all the other words. We take the query of novel, and we do a dot product with all the keys of all the other words. Okay, so this is the blue and the red one. And this gives us a scalar, which is this scale that says basically how important is all the each other word for novel. So here optics is very important to understand novel. Okay, you see? And then we do a weighted sum of all the values by this importance thing. So optics, we have a strong importance, and novel small. And this, oops, yeah, and this gives us a vector. Okay, so weighted sum, and this gives us a vector for each word. So comedy was also combined with the other words, and every word was combined to make like a contextual state. Now, sometimes you have several words that are important. For example, novel optics is important, but award is maybe also important, but for another reason. So the way we do that is to have several of these things made in parallel. So it's called a multi-head transformer. So this general process is called attention, because you compute the attention that each word should have for every other. And this is called multi-head attention. So we have several contexts, we combine them all together, and then we do some deep learning magic, which is using a nonlinear activation function, just because if everything is linear, it usually doesn't work. And yeah, we have shortcut connection, but this is not important. And then we have a new vector for each word, in which we have integrated the general context of the sentence. Okay? Yeah.
So you're not using the location information in the within the sentence?
That's a good question. So I have a slide about that. Okay. And then we do that several times. So this is like, we mixed up several times. So in our case, we do that 12 times. So 12 times, we take again the vector that's associated with each word, and then we mix it again to all the other words. And this gives us at the end a last vector for each word. And what we want to do is that we want this vector to be the one for the next word. Like the vector that's at the end of processing novel should be community, okay? Which is the next one. Community should be a was, and optics should be this last word, which is significant. Okay? So here there's a little problem, which is that if you mix novel with community, here, then it's quite easy to guess its community at the end, because you already put that information in your vector. So to avoid that, we actually use a mask, in which each word is only mixed with the previous word on the left. For example, community will only be mixed with novel, and then optic will be mixed with everything. Okay? So this is called causal attention. And this general process is called language modeling, because what we end up doing is learning a probability of language itself. So if you have the probability of all the words, you can actually write that as the product of the probability of each word given the previous one. And here you see we've got all this information. This is the context, and this is the last word. So we're actually modeling in a statistical way language, which is, some people don't think it's possible. That Chomsky was really against this idea, but that's what we're trying to do.
Thomas?
Yeah.
The way you combine or you mix the words to the left, is it something that that works with the English language, but that probably would not work with another language? Or
yeah, there is
something that you can generalize.
There is another question. So, so all languages are sequential. So this ID, the general ID, works for all languages. But then the vocabulary itself is you have to build one for each language, and you have a smart way to combine languages. Because usually what we do here is that we won't really use words. We will cut words to use what we see also when we learn linguistics, like prefix, suffix, and so we can reuse things. For example, when you say constitutional, like you can reuse the knowledge of constitution. And so we split these words. And so usually when we do multilingual thing, for example, what people are doing today is that they are cutting things, and they are actually prefixes that work for several languages. So when the languages are close, you can manage to have a common vocabulary. But the further the languages are, the more difficult it is to use a single model for several languages. For example, usually when you do very big model for a lot of languages, you would still split the Asian languages. For example, Chinese, you would do another language because it's so different that it doesn't mean anything to learn the same language. But this general process is really robust. And there is one important caveat with transformer that you were saying is that they are not sensitive to word ordering. What we did here, this weighted sum, it doesn't really care if optics is before or after novel, which is obviously a bit strange because for us it's very important, otherwise it makes no sense, right? So this model as this is not sensitive to position of the word. And so this is really bad. And the way we solved that is that we had another vector which is indicative of the position. So this one is saying novel is the first word. This one is saying this is the second word. Okay. So this vector, they just sum. It's just a summation. Here we just sum this little thing. And the brown one, the bottom, we have will be there to indicate the order of the word. Okay, this is, that was a way to do that. That's the common way we did that. So yeah, that's the model. And now let's train it. Okay.
Can I ask why the name of this model is transformer?
Yeah, you can ask.
Okay, so why is that?
No, yeah, because actually, yes, we'll talk about other models which are more common. Actually, a lot more used, which are recurrent neural network and LSTM. And transformer was a bit is very recent. This model is super actual, and it has the specificity that it will take. For example, here it will take 7 words as input, and it will output also 7 words. And if you know about the context of the field, this is very strange. Like people don't do that usually. And so we call that transformer because it transforms a fixed number of tensor in another fixed number of tensor. But yeah, also it's very flexible. People have been using transformer also on optics, computer vision, and you can also use that for speech recognition. You can use that for a lot of things.
But in general, do you use the transfer learning as well? Yeah, in this work, the transfer learning itself.
Yeah. So that's totally different. Yeah, there is a common part of the name, but there is just no relation at all.
Yeah.
So transformer is just a very general model that can transform one matrix in another matrix. So that's so we're training with this language modeling objective. Now you know this. I'm really happy because you know now a lot of very precise terminology. So how we build an input? You remember it was a sequence of words. So how we build that from all this thing where we just put them, we just concatenate them. So we have the personality, we put the personality sentence one after the other, then we put the dialogue history, and we say, hey, hello, how are you? I'm good, thank you, how are you? And then at the end we have the details we're going to generate. Right? So it's very simple, we just align everything. Our knowledge, our history, our user. And you see the last word is missing, it's game of throw, if you are familiar, because we're trying to generate this, okay? So to train our model, we will indicate the answer, the real answer, which is Game of Thrones, and this is called the label. So we have our inputs, the transformer model I show you, and it will generate outputs, and for each word, it will try to predict the next word. Okay. So we train that by doing prediction. We compare the prediction to the label, compute the error, and then we have some algorithm that called backpropagation that will update the weights inside the model. Okay. Now I'm moving to transfer learning. Are you okay with what I say right now? I mean, if you have a question, it's the last time before we dive in something else.
Yeah. I mean, it's still very much based on just collocations, right, of words. It's not, there's no actual language model yet, right? It's just the statistical occurrences, co-occurrences of the words.
Yeah.
Yeah, this maybe like.
So yeah,
this could be incorporated in some way. Or?
Yeah. So it's also what is very surprising actually is that we can go very far with purely statistical method. I would say, yeah, this word is next to this one. So and this kind of model that uses its collocation in a very wide sense because these inputs are very far, they're very big. I mean, they can be 500 words. So it's not just I said this word, so the next word has to be. It can be I said this word 2 paragraphs ago, so the next word should be the same. It has a very wide range of view. But it's still purely statistical. Yeah. So what is very interesting right now is what we call the grounding problem, is how you relate language to other things, like for example vision, or like real life, you know, like acting in the real life, which is how people are trying to go behind this statistical paradigm. Well, it will still be based on a statistical method, but then we will try to put some idea of what is a cat as an object when you say the word cat, you know, like, so that's maybe what you're talking about. I'm not sure that's what you're asking, but that's one idea to go behind just language as a statistical way.
Yeah, then an actual relationship between the meanings of words, right? The kind of like, what is it called, word net? Kind of things.
Yeah, so that's exactly, that's another branch of research, which is based on more linguistic theory.
Yeah, exactly.
Yeah, okay, so that's also very interesting. There's a lot of work on that, and actually, just you will talk about that, so maybe I'll let you talk about that. That's also very interesting, because right now, we feel that something is something more symbolic approach would help, and that's something people are doing. That's not what we are doing in this work, but it's also very interesting. And there are big debates here. Like, can you learn this kind of very formal general representation of language from data only? There's a big debate. I don't think so, but some people think so. And it's very interesting. Now, back to our problems. Now we know how to learn to generate words. But the thing is that it doesn't work. So that's too bad, right? Why does it not work? Because personal chat, as I said, it's very big, I told you, but it's still very small for what we want to learn. Because if we want to learn to do dialogue, we need to learn topic coherence, dialogue flow, coherence resolution, a bit of sentimental analysis, like if you say my dad is dead, then you should be a bit sorry or something like that. You should learn textual entailment, which is something implies something. Well, all this notion, you have to learn all that just from this million of words of personal chat, and it's really not a lot. Usually the models we use for this, all these things are specific tasks in NLP, people have been studying them separately, and all the dataset for this are at least the same size as our full dataset of dialogue, but they're also work. And we usually use a lot bigger dataset, for example, the billion word dataset, which is well called because it has a billion words, so it's a lot bigger. So when we try to learn everything from our simple dataset of dialogue, we fail. Why is this a problem? Well, this is an example. So this was the competition we were last month. So we won we won one track of the competition. This is us at the top. Just showing this to be a bit proud. But there is a problem. Here is an example. You have two parts usually to these datasets. One is the public part, everybody has access to it, and there's a private part, which nobody can access, except the organizer. And usually what you do is that you tune your model on the public part, you do as you can to make it the best model on the public part, then you send it to the organizer, you cross your fingers, then you pray the God you have, and you get the results on the hidden datasets. And when you learn from a small dataset, what will happen is that if your model is super powerful, it will really fit well to this small public dataset, and it will fail to generalize to anything that it has not seen. Basically, it's so powerful, your model, that it will learn all the specificities of your examples, but then it will forget that there are other things in the world. So this is called overfitting. And the team part here was strongly overfit, so they get super good results on public dataset, and then they are super bad on private dataset. And the way you can avoid that, usually, is to have a model that's less powerful. And then you have medium results on the public dataset, but you also get medium results on the private. So how can we escape this? So what we do is transfer learning. Transfer learning is a unicorn. So it's a two-stage procedure. You first pre-train your model on a very large dataset, the largest you can find, which obviously won't be exactly the one you need for your task, okay? Because you're just taking the biggest one you can find. But you hope it will learn some general concepts of things, and then you fine-tune your model on your small dataset. So in our example, we used a dataset called Toronto Book Corpus, so it's 7,000 books. So that's a lot, because a book is already a lot of sentences. So when you take 7,000 books, you have a lot of words. And you just learn to do language modeling on that. So basically we teach our models to generate books. So most of them are like romance and fantasy books, so it has a tendency to talk about love and unicorn. But it's okay, I mean, learn some useful concepts in the And then it will build some kind of what we call word knowledge. For example, it will know that when you talk about unicorn, then probably you talk about dragons. So it learns this kind of thing from generators. All these books, they are like open books that people could not get published, and they could just open access on the internet. That's how we build it. And then you fine-tune it. So then, after your models know how to generate books, you say, okay, now we're going to talk about dialogues. You give your model the personal chat datasets and ask it to generate dialogue. And you have to do two things that will go. One thing is you have to adapt your model a little bit, because a book is like one person talking, the dialogue is like 2 person talking. So you have to adapt a bit. So the way we adapt that is a lot of talk, but you can just look at the graph. So we have this input. The gradient is the positional embedding we were talking about, that say this is the beginning, this is the end, and we add some additional embedding that say this was person 1 talking, this was person 2 talking. So we do this, we add another information to the dataset that we will know. And then I switch this. And then we will learn also a notion, more general notion of dialogue flow, which is we will give it 2 possibilities. One is a good one is a bad one. So here the bottom one is the thing you should study. For example, if your personality is I like to ski, well, that's a really short personality. And the other person is saying, hello, how are you today? You can answer, I'm good, thank you. So that's good. But you can also give a bad answer. Like you can answer, you have a nice dog, which makes no sense. And you will train actually your model to classify this. You will train your model to say, oh, this is a bad way to answer something. This is a good way to answer. And through this process, it will learn dialogue. So this is how we got these strong results on the automatic matrix. And now the question is, what do humans think about these models? So these are conversational models. So they are made to talk with people. So we try to make them talk with people. Well, the people. This all happened during competition last December. And so they asked also again mechanical Turkers to evaluate models, to talk with models and say, okay, this one is interesting to talk about, to talk with. This one is not. And what happened is that we were quite good. This is like the ratings, but we were not the best. We were second. And this is a bit strange because on the automatic matrix we were really, really far above all the other team. But on the human evaluation we were not the best one. How does the conversation look like? It looks like this. This is an example. So the bot is in blue. So the user say, yeah, I like rock climbing. Do you have any hobby? I like nature. Do you? I do love nature. What is your favorite rock? Mine is rock. Okay. Then the user say, well, I like rock music. Does that count? I think it does. What do you do for fun? I work at a restaurant that I love and rock climbing. That sounds fun. I'm into nature. Cool, so I am. Do you have any pet? Do you have any pet? So the conversation is okay. I mean, it makes some sense. But there is one big problem, which is it asks a lot of questions. Well, this is maybe not the worst conversation. To show that this is the user feedback. And what really came out is that our model asked a lot of questions. And asking some questions is okay, but like every sentence replying by questions feels like strange to humans, right? And when you look at the numbers, it's really, you can see that. This is our model, Hugging Face. This is the number of who, what, when, where that are in the answer, and there are a lot compared to the other models, and also a lot compared to human. You see, human, they say that every 10 words question, or I think it's 10 sentences. And this is also the number of question mark, and our models really ask a lot of questions. So that was bad. And that actually raised a more general question, which is how I'm going to end my talk, which is that the automatic matrix that we have, that I showed you on the tables, on which we were really the best models, don't correlate well with human evaluation. So that's an open question. Nobody really knows how to design matrix that can be computed automatically, and that would correlate well with how human judges natural language evaluation. So we are doing a workshop on that next year with Microsoft and a lot of people. And yeah, if you happen to be at Minneapolis, I hope we'll learn a lot about this. That's it for today. Thanks for listening.
Thank you, Thomas. Do we have questions? More questions?
Excuse me.
Do
you consider the question mark as a word?
Yep.
How do you like assign a question mark at the end of the sentence?
How do we
generate the question?
Oh yeah, like a word. So punctuation is like words.
So every punctuation is.
Yeah. We have also an embedding, and we also generate. It goes all the same way as a word. Yeah.
Thank you.
So actually the winning team here lost in conversation. The winning on the human evaluation. They had a lot of post-filtering, which we should probably have done too, which is you filter the answer. If it has too much question, you sample another answer until you get a good thing. And that's something I didn't want to do because yeah, automatic metrics were good. But that's usually what people do with these models. After that, they really process the answer a lot. They cut some part. For example, this repetition here. Do you have any pet? Do you have pets? You can very easily detect that. just remove it. That's what they did. I think it's not very interesting to do that, because that's not, you don't learn a lot by doing that. Well, I mean, you don't learn a lot on language. I would rather learn why my model generates this thing than just cut it.
Do you have any idea why you generate such repetition?
Not really. Well, we're trying some stuff, but it's still very open. It's a common problem of all these language models. They tend to repeat themselves. And they also tend to, so this doesn't have this, but another problem is usually they tend to say, I don't know. Because it's a safe answer that works almost every time. So they're sure that they will be safe with this, so they usually say, yeah, I don't know. And so these are the two main problems people are trying to solve. And also the avoiding contradiction. Like they tend to contradict themselves. They would say, I'm 21, then you ask, what's your age? I'm 17. But you say you were 21, so that's the other problem, but yeah.
The model is constantly learning, no?
No. Learn once, then stop.
Okay, so you're not through the discussion, you're not you don't keep learning with the answers that you're...
So what you do is that you store the memory, the basic memory, and you use that as input, but you don't learn from that. Yeah. Well, you can do that. So,
at least that would be a good incentive for asking questions. I mean, you could always say, well, the model is still learning, so therefore it's asking questions. But this is not the case. Yes?
But it's pretty strange that it's repeating itself, right? Because it uses the whole conversation as a history, and then in the real life, I don't think there should be a lot of repetition. There wouldn't be a lot of repetition, so I think it's pretty strange. Something is wrong.
A lot of people have been,
You just repeat it yourself.
I mean, a lot of people have been thinking about that, and just nobody has a clear answer to that today. Well, I haven't seen a very convincing theoretical explanation for that, because that's true in the book. You do have some repetition, but not this kind of repetition. For example, the nouns, often you don't repeat them.
Yeah, you could like manually put some penalty or repetition or anything, but as you said, that's kind of not what you would want to do.
Yeah, you don't learn anything when you do that.
Knowledge you want it to be learned.
You would, yeah. So usually what people, one interesting thing, which is a bit like that, but more smart, is to work on what we call the decoding. So how do you generate this sentence is that actually you keep a range of possibility. Like for example, you will sample several first words, and then from these first words you will sample several second possibility. You leave some tree, and you keep the best. Because sometimes you say a word that have a low probability, that it's a rare word, right? So it's not often said, but the word you will say just after is like very common word. It's like a very good word. So you have to wait a little bit sometime and say, okay, this word is not the best chance, but maybe it will lead to a good path of conversation. So that's what we do. This is called decoding. So you keep a beam of possibilities, and you keep the best one, and then until you have reached you've reached the end of the sentence. And you can learn this kind of decoding, and you can make a statistically learned decoder that will say, oh, I'm starting to repeat myself, so these beams should be avoided because they are the same as the previous ones. So this is one area to do some intermediate thing, like where you're not cutting this with a rule-based system that's stupid because you're just putting your rules, but you're trying to learn the way you generate a sentence from this thing. That's really hard. Maybe it's not super clear how I explain, but that's one area where we could do something.
Yeah, so for these chatbots, they are an online version or offline version? Because I know some chatbots that they really connect to, for example, Google, or some kind of billboard. Okay, what's the hottest topic of today? So they try to pick up some keyword and continue the conversation. But whether this is also abstracting the information online?
Yeah. So here, all the thing I taught here is like a single competition that happened last year. So you could not connect to external database. It was like forbidden. But now people are trying to make this. One reason we think these chatbots are a bit boring is that they don't have a lot of knowledge. They don't have access to knowledge that would make them interesting. So people are now starting to, for example, use Wikipedia as a basis for talking. For example, instead of just talking in, just making in general small talk like this, you have a Wikipedia article about a movie, and you're talking about this movie. So you have some information, some knowledge, and you could use, for example, access to Wikipedia or to.
But this also depends
but
on
that's not, it's not.
what kind of personality you want to put on this robot, right? For example, if you use Wikipedia, it's a little bit academic way of talking, and if you use some other knowledge, for example, some other forum that's more for young people, so probably they could come out more like different characters.
Yeah.
That's also the future of that. That's you can choose what kind of robot you want to talk with.
It's very interesting. Also, one thing people do is maybe you know the ocean model, which is a psychological model. Let's say you have 5 big personality aspect, which is how extrovert you are. So there's a very well-known model. It's called ocean model, and people are trying to make chatbots that have personality that they can design like this. So this chatbot will be more expansive, this one will be more shy, and you can try to do that and see if you can generate a conversation that would be conditioned on this thing. So people could recognize, say, oh yeah, I'm talking with a shy robot, for example. So there's interesting research in this area. Yeah.
Well, we have presents for you. I have a small story about the presents. So we usually give some 3D printed sculpture to the speakers, but apparently the 3D printing facility of the presents part, the printer is broken. Therefore, we have only one sculpture and we replace the other one by a box of chocolates. And to avoid fight between you two, I decided that the best would be to actually ask Hugging Face to decide who should get the chocolates and who should get the sculpture. So I registered to Hugging Face, and I learned that I was the 1,700,000 user of the service. And I really have to share one important information with you, because at some point they asked me for my age, or I should say she has a name, Maeva. She asked for my name. You can choose what's the gender of your chatbot if you want.
Of course you're choosing.
No, I didn't cheat. And she replied, because it said that she was shy. Most of my friends are younger, so bear with me if I chat weirdly with you. So that's the answer I got. Yeah, when I said my age. So it's pretty accurate, I would say. Anyway, despite all my efforts to actually get an answer, Maeva refused to tell me if you should get the chocolates or the 3D printed sculpture. So you will have to fight, both of you. Just leave the presents on the desk. Anyway, we have a small break, like 5 minutes, and then we'll just take the lead.
You can fight outside, okay?
Yeah, you can fight outside.